With the formula in hand, we can now analyze how adding one more explanatory variable affects the standard error of beta j hat. It is equivalent to finding how it changes the estimated variance of beta j hat. Adding a new variable makes the changes in two opposite directions. On the one hand, the residual sum of squares, SSR, will reduce because the new explanatory variable helps to explain part of the variation in the outcome variable y, leaving less variation for the error term. In large samples, the degrees of freedom converge to n. The estimate of the error variance, sigma square hat, decreases in large samples. It will lead to a smaller estimated variance of beta j hat and a smaller standard error of the estimate. However, on the other hand, adding a new explanatory variable could exacerbate the multicollinearity problem, which means the new variable could be highly correlated with xj, leading to an increase in the rj squared. Generally speaking, we don't know which effect dominates. Notice that the total sum of squares of xj, SSTJ is unchanged. There is a special case in which the new variable is not correlated with xj. In this case, the rj squared will not be affected by the new variable. In other words, the new variable does not introduce multicollinearity. As long as the new variable has some explanatory power, the estimate of the error variance, sigma square hat, will drop, and therefore the standard error of beta j hat will fall. A smaller standard error means a more precise OLS estimate, since its confidence interval becomes narrower. The t-statistic becomes larger, and the OLS estimate becomes more statistically significant.